So, very good morning to all present here. So, we are about to start the day 3 session, and today we have the guest of honor, Dr. Y. Ravikumar from Presided Warangal. So, he'll be introducing you to the metal 3D printing in detail. So, once again, I welcome all the participants to join up for the morning session from Dr. Y. Ravikumar. Over to Pradeep to introduce the speaker.
Good morning to one and all. Before we move to the first session of day 3, let us welcome Dr. Professor Y. Ravikumar as a resource person for the session to this virtual FDP. It's my pleasure to introduce Professor Dr. Y. Ravikumar before you. Dr. Y. Ravikumar is Associate Professor in Mechanical Engineering Department at NIT Warangal. He obtained BTech degree in Mechanical Engineering from JNTU, Kakinada in 2000, ME in Computer Integrated Manufacturing from PSG College of Technology, Coimbatore in 2002, PhD in Mechanical Engineering from Uspania University, Hyderabad in 2011, and postdoctoral research in 3D printing at Milwaukee School of Engineering, USA in 2012. He has supervised more than 30 MTech projects and produced 4 PhDs and guiding 4 more PhD theses. He has published more than 70 research papers in national and international conferences and journals. He has filed 1 international patent and 2 Indian patents in the area of 3D printing. He is instrumental in setting up rapid prototyping laboratory at NIT Warangal. He started MTech program in Additive Manufacturing in collaboration with the Central Manufacturing Technology Institute, CMTI, Bengaluru. First time in India of its kind. He has established a world-class metal 3D printing facility at NIT Warangal under TechCube 3 brand. He has conducted more than 15 training programs across India and trained around 900 participants in the area of 3D printing. He received Young Engineer of the Year 2009 award from the Government of Andhra Pradesh and the Institute of Engineers India. He has executed sponsored R&D projects worth of 1.24 crore rupees in the area of 3D printing. He is the life member of ISTE, IE, and RPSI societies. With this introduction, I would like to welcome Dr. Y. Ravikumar to this FTP. Over to you, sir.
Yeah, very good morning, one and all. First of all, thank you, Dr. Pradeep, for your introduction. And I would like to also thank Dr. Lijo Paul, the coordinator of this program. And I would also like to thank the management of St. Joseph College of Engineering and Technology. And of course, KTU for the sponsor this event. You might have exposed to this technology, the exciting technology called 3D printing.
Yes, sir.
Yeah, and during this session, I'm going to present you the recent advances in metal 3D printing technology. So coming to the outline of my presentation. So let us start with the steps involved in 3D printing process. Just a quick introduction to this 3D printing process. And we'll be spending some time on the material and the material aspects of 3D printing and metal 3D printing. So you may wonder why I kept all these 7 processes as being listed here. So under the metal, so you may wonder. If you see the scenario of this 3D printing, formerly known as rapid prototyping. So this journey was started with a process called stereolithography operators. So that will come under VAT photopolymerization process. People used to print only polymers. I'm talking about the inception of this technology, that is late 80s and early 90s. The journey has started with polymer printing, but slowly it has been capture the attention of manufacturer rather than a designer used to use this technology for validating his design in terms of making a prototypes. But then this technology has gained a lot of attention of manufacturers also. So then if you come to the technological advancements, even a VAT-based photopolymerization system now even could be able to generate some extent metal parts also, ceramics also. So we'll see this metal 3D printing, though predominantly some specific process like powder bed fusion, it is very popular for the metal printing, and even a directed energy deposition. It is another technology which predominantly or produced metal parts. So that is directed energy deposition, powder bed fusion, and sheet lamination technology also. And recently, material extrusion process and binder jetting processes can also print metal parts. And the same case for the material jetting technology. So my talk titled to metal 3D printing technology. But the metal 3D printing is not only confining to a 1 or 2 3D printing processes with the recent developments, but it need not be in a single step. It may be quite possible, maybe with 2 steps. Sometimes it may be 3 steps, 3-step process to get metal parts. But processes like powder bed fusion, directed energy deposition, sheet lamination process are predominant. In a single step, you can get your metal part. But whereas it is quite possible to get the metal parts printed with each and every processes, which will come under this category ASTM classification of 3D printing processes. And finally, we will see some of the fabrication challenges of this metal 3D printing technology. So that's what I have planned for the next 1.5 hours. I have planned the session in this way. So if you see the steps involved in 3D printing process, so first, check what is your application, what is your product. The product may be a simply a coffee cup, or an automobile, or an aircraft. But the application and the requirements may be different based on your application. So your requirements may be different. But whatever may be the application of your product, so first we need to start with a CAD model. So that is a digital data as a input, which we should bring our product into a CAD model, a computer aided design model, either a solid model or a surface model. And that model should be in a representation of a triangular mesh file, so-called STL file, stereolithography tessellated language called STL. And that STL file, which it has been imported to a interfacing software, which it will be connected to the printer. So you have an interfacing software. So that software will take this STL file as an input, and we need to specify the process parameters. Say what could be the layer thickness. As we know that basically it is a layered manufacturing process. We need to specify what could be the thickness of the layer that you are going to fabricate. And if it is a laser driven technology, so we need to specify what could be the laser power, what could be the laser scanning speed, what could be the, say, other parameters. It depends on if it is a laser driven system or if it is simply a heater or a thermal energy or a chemical energy. So accordingly, we need to specify the process parameters. And once you specify, and another important thing is a orientation. So orientation will affect your quality, build time, and other requirements. So which we need to carefully select these process parameters. If you are not selecting, by default software will take some value, which is ranging. Typically, if it is a layer, the layer thickness, it may be 0.05 mm to 0.5 mm. Again, it depends on what kind of technology that you are adapting. So once you specify all these process parameters, and your software will automatically generate a code, something like G and M code in case of a CNC technology. But we are not writing any code, but the software will automatically generate a machine setup. So that machine setup, so that set of instructions will be sent to the machine. So as for your instructions, the cross sections or the layers, so within the machine, the physical realization of those layers, one layer upon other layer, so it is getting stick together. So finally, from the first layer to the last layer, so your component is ready. So once you have done your fabrication inside the machine, and we need to remove that workpiece, or we need to remove the component from the substrate or the platform, we need to remove that. And while removing, so it may have some support structure right now, where you can see there is a support structure where it requires, wherever you have some overhanging portion and wherever you have at the base, at the platform, which we need to give some support structure. So that should be removed. And once you remove that, and cleaning should be done. It depends on what kind of 3D printing process you are using it, and based on that, you may have a different, say, solvent kind of support removal system, or a physical breakaway kind of a physical breakaway of a support structure. So once you have done all that stuff, and we need to even post-process your component. Why we need to post-process our component? So again, that dictates the application of the product. If the application demands high quality or high tolerances if you are looking at. So then accordingly, we need to use some post-processing method to enhance the quality, maybe in terms of mechanical properties, in terms of metallurgical properties, sometimes which we need to subjecting to a furnace treatment, or which we need to enhancing the density sometime. Then we may use an appropriate post-processing technique to suit your product for your specific application. But this application may not demand you much if it is simply serving a coffee in a coffee cup. But you imagine that if it is an automobile engine, or it is a jet engine which has been used in a aircraft, so then you need to have a stringent post-processing or certification. Sometimes we need to say generate for that. But anyway, so in a nutshell, so these are steps involved in any typical 3D printing process. Then we'll further proceed to the next slide. So coming to the metal 3D printing. So even it is a metal or a polymer or a ceramic or composite, so the process remains same. And if you talk about, say, we have a metal 3D printing facility at NIT Warangal, we are using a 3D expert software, so that is supplied by 3D Systems USA. Basically, this software is responsible for preparing the build setup and optimizing support structures, orientation, and we need to simulate it before it send it to the printer. So it should capable of simulating the tool paths, or simulating sometimes maybe which it may subjected to some warpage, shrinkage, that we'll discuss separately. I'm going to discuss some of the common defects that you come across in metal 3D printing process. And if you have some simulation stuff here, which we can even minimize your wastage of material or wastage of man hours. So if you're not done properly homework while generating your tool paths, or even your post-processing will become very tough once your design for additive manufacturing. I'm using a word called design for additive manufacturing. So what do you mean by design for additive manufacturing? You know, design for manufacturing, DFM. The same logic can be extended for the additive manufacturing here. So the ease of fabrication, your design has to give an opportunity for the additive manufacturing or 3D printing machine to ease of fabrication without much errors, or the cost, the economy. So then how do you achieve that? So definitely we need to do that stuff before you send the code has been sent to the machine. So maybe we need to position your model in the organization of your build chamber, and creating the supports. Then creating the supports is going to play a vital role for the metal 3D printing system. Why? Because if it is a polymer, so basically you have a polymer model and support, both will be polymer. But here metal, so even support is also same material. If it is through a powder bed system, you don't have an opportunity to change your support material differently in a powder bed I'm talking about. So, but it may be, it may not be true for other processes, but when this is basically a powder bed system, which I'm going to explain this workflow. So which we need to create the supports, which it should be easily removable, and it should give a proper thermal conductivity also. Not always the supports are curves, but it will help you to some extent to have thermal conductivity, uniform thermal conductivity. Even supports can also responsible. So which the importance of the support structure and the orientation, as I said previously. So the positioning and the orientation and modification, if at all some errors are there in your STL file, or we need to modify the design, so then we need to do that one, and then we need to create the supports, and we need to sometimes optimize the structure of your product, and we need to simulate the builds, and we need to optimize the technology. Just don't think that it is a push button kind of approach, especially metal printing, but it may be the case for polymer printing, but it may not be the case for a metal printing, which we need to do a lot of optimization, a lot of simulation before it's sent to the machine. So we do calculate the scan paths or the laser paths and arrange them and sending it to the printer, and before it even started, and even you can do a post-process requirements which you can do. So your post-processing, sometimes your post-processing cost may be 50%, 60% sometimes. So then, which we need to reduce our post-processing efforts. So that is through your design modifications, if at all it needed, support structure optimization, build orientation optimization, simulation, some extent, which you could able to reduce your post-processing cost and the post-processing efforts. So altogether, what I'm trying to say here is we need to do a lot of stuff. If you are looking for the economics of it, like simply if you want to print with the default parameters, but it will print, sometimes it may failure also, build failure may also happen. But the thing is, which it is a better practice to work all these areas, and then will you make use of your machine at the optimum levels. That's the thing where I want to discuss with you. So this with this workflow, then we will talk something about on the material side. So whether all the materials can it be 3D printable? Say if you talk about engineering materials broadly, you have a polymer, and again you have a thermoset, and you have a thermoplastics and amorphous, and you have polymer group, and you have a metal, and metal alloys can also be processed through additive manufacturing or 3D printing process. And even it can be the case for the ceramics, and it can be the case for the composites. So, and all these four standard engineering materials is quite common in 3D printing. And then we do have a functional materials, like it can be an electronic or a shape memory materials, which it could have some specific functionally graded materials. You have some specific functionality. So those materials could also be processed through additive manufacturing or 3D printing. So apart from that, you can even process some natural materials. It may be a biological material. So it can be a, say, even now people are targeting to argon printing. I hope you have some medical sessions also. Maybe today, I don't know whether you have completed, but you can even print them, living cells or tissues can also be, or scaffolds can also be. So then you have, or even a food can also be printed, or even it can be a construction waste, or even it can be any sort of material that you are looking at. Apart from the standard engineering category of materials, it is quite possible with other materials. And then what could be the feedstock form? So the feedstock or the raw material could be a powder, granulated powder, or a filament, or it can be a wire or a rod form, or it can be a sheet, laminates, or even it can be a liquid. So these are the four commonly used feedstocks for 3D printing. And then, as I said, like ISO and ASTM, so they have standardized this classification into 7 groups, and that is 5290015. So as for that, it has been classified into 7 categories. So and further discussing with the feedstock of the 3D printing processes, like you have the feedstock, the physical type when you fed into the printer. So it could be either a liquid form, or even it could be either a powder form, or even it could be either a solid form. And that is before you fed into the printer. And once it has been fed into the printer, so then what could be the principle behind, say, how your raw material is getting processed, right? So then sometimes it may be through a chemical reaction like polymerization, or sometimes it may be simply a jetting principle, inkjet, or a binder jetting principle, or sometimes you may be atomizing the powder or even a liquid. So you can see some cross connections, not one to one, so which we can notice the developments, multiple materials or multi-form from one form to other form. Maybe it is quite possible. That will enable you to go with a multiple material, or a functionally graded material, or even it could be a sort of composites can also be possible. So which we have a powder maybe atomized, or powder maybe melting and solidifying, or if you have a solid material, so even it could be a joining process, like simply like a welding. It can also be joined, your solid raw material. So your solid raw material, sometimes it is getting melted and solidified also, right? And by making use of this principle, and then you may finally say your feedstock. So after applying some sort of energy, and which you are even again getting back liquid or a powder or a solid form, or sometimes it may be, which we can see some powder atomized, and then it is to liquid form, which it is coming, right? Say then it's a combination of powder plus liquid. It's also possible, right? So which you can, we will discuss thoroughly how maybe a metal powder, maybe a ceramic powder can also be, for example, for VAT system or a material jetting system, which could be quite possible. But anyway, so then which you can have these 7 groups of 3D printing processes. So either it should be a liquid getting polymerized and through a VAT system, or a ink or a binder maybe jetting and then getting processed. We'll discuss further how it is getting, say, and this may be through jetting technology, so which it is jetted, either a material or a binder could be jetted, or powder. The raw material is powder in case of a binder jetting, but even you are jetting the binder. So you have 2 things here. So binder is also jetting, and the raw material is a powder form is also coming. So which should be. So the powder particles are getting stick through this binder that it has been, say, sprinkled, or it has been jetted from the nozzle. And then you have the material jetting system, powder bed fusion, so where again the powder. So broadly, if you see, the powder could be the form for the binder jetting technology, or even it could be the form for the powder bed fusion, or even it could be the directed energy deposition. And coming to your binder jetting, so it could be a liquid, or it could be even, say, powder form. And coming to VAT system, only one, that is liquid. And coming to the solid, where even it could be predominantly sheet lamination and material extrusion process, the raw material in a solid filament or a rod or a strip, or even it could be a sort of a DED system, which you may be using some powder can also be used as a raw material for the DED system. Even a metal rod can also be, or a metal sheet can also be maybe the raw material for your directed energy deposition. So with this discussion, so we will focus on the metal printing aspect. Before we start into metal, and let us understand, I don't know whether the previous speakers might have talked, but anyway, so it is, we cannot bifurcate, like let us know first the polymer. Why? Because that was the technology where this was started. And if you see, and why I'm quoting this as a single step or a multiple step. So within a single step, so if you want to make a polymer, so basically the type of material is a polymer, right? So then how do you get bonding? The bonding or the state of fusion may be through a thermal energy, thermal bonding, or a chemical energy or chemical reaction, so that has been taken place. So, and this is a state of form, the fusion or the bonding. And you talk about the material feedstocks. So you have a filament material, and how that filament material is distributed. So how the material is distributing from the feedstock to the machine, that is through a deposition nozzle in case of FDM or in case of extrusion based melting system, right? And if you come to say, again, you may be using a thermal bonding, so where your feedstock is, it is getting melted. You are melting the material, and that is coming from the print head. So it is getting jetted from the print head. And even you do have a multiple jetting. So the advantage of material jetting system, so you do have hundreds of jet heads, something like your inkjet system. So which you have a multi-jet material printing in case of a material jetting system. So, and then this is about the feedstock, and then how you are distributing the raw material to the machine, and the basic principle involved. And if you are talking about say the powder form of material, so that powder form you create, you pile like a bed. So you spread and form like a bed, and among that bed you selectively fusing the material powder particles, that is in the powder bed fusion process. And if it comes to say you have a liquid, and that liquid in terms of binder, so it is getting jetted from the print head, and the raw material is a powder, so which your powder and your binder, so it will be creating the fusion of the powder particles through your binder. It is getting a bonding, so that is the binder jetting process. And even you do have material jetting can also be done through a liquid based material. So you have a print head. From the print head you will be jetting that liquid, and basically you may be using here is a chemical reaction, means basically it is a UV sensitive resin, that is a photopolymer resin, so which it is exposed to UV light, so which it will start curing or start what you call solidifying. So that is the case for the material jetting as well, a VAT based system. And you have the sheet material as a feedstock, and it is distributed in terms of stacking these sheets, stacking these tapes. It can be a metal tape, or even it can be a paper simply, or even it could be any other laminate that you're trying to stack it, and then fusion of the stacked sheets, and that's what you'll do in a sheet lamination process. So all the 7 processes could able to process polymer in a single step. The underlying thing is a single step. In a single step, you can process polymers through all these 7 3D printing systems. But whereas if you talk about metal, I'm talking about in a single step. So if you want to process metal in a single step, but all the 7 processes are not supportive, which you can see I have listed only 4. So that to a single step I am talking about. But if you add one more step, maybe furnace, maybe you can add the furnace treatment, debinding, sintering, infiltration, even it may go a multi-step. That multi-step, all 7 processes are eligible, but single step, but maybe predominantly 4 processes are responsible for metal printing. So as we are talking about the metal, so the material type is, of course, is a metal. So that metal, either you bring it in a powder or a rod or a sheet, it can be a laminate, it can be. So your metal, once it has been, say, taken, and what kind of a fusion, like the state of fusion, so it can be through a melting at the melting stage itself, or solid plus melted state, or only solid state. So it is possible. So you have a melted state condition, or you can solid plus melted state, or solid state alone. So it is quite and then coming to these material feedstocks, as I said, it can be a filament, or it can be a wire, or it can be a powder, or it can be a sheet material. And how do you distribute your feedstock material to the machine? So you may use a nozzle, deposition nozzle. So that is for the ED system, or that is even for the material jetting system. So these 2 systems, which you will be basically you will be depositing the feedstock material from the nozzle, right? And the basic principle involved here is you will be selectively depositing the material to the substrate. It is something like welding. So it is very similar to the welding, especially if you talk about this technology, right? Then the other important thing is the source of energy, or the source for the fusion. The source for the fusion, either you can use an electron beam, or either you can use a laser. Laser is the most frequently used, but in the recent times, electron beam and induction heating is also, or even it could be plasma, or even it could be it could be any form of laser source, laser or electron beam, or inductive heating, or a plasma. So it can be anything. But here, whatever I mentioned here, it's predominantly used laser, electron beam, and induction heating, either a DED system or a material extrusion, material jetting system. And if you talk about your powder feedstock material, so you may create, instead of depositing through a nozzle, so you will be creating a bed of powder, and you will be selectively fusing the material from the bed. And then again, you may use a laser as an energy source, or an electron beam as energy source. So that is for the powder bed fusion technology. And if you talk about a solid state fusion, so then the feedstock could be a sheet material, and you will be stacking. So how do you distribute your feedstock? So by joining these, or by stacking these sheets, and then you will be doing a fusion of the sheets. How do you do that? So if it is a metal, it is through welding. So you will be using an ultrasonic welding technique here to join your metal sheets, if it is a metal. Or even it could be clamping, or even it could be any sort of joining that you come across. But typically, you may use an sonic welding. Sonotrode will be used here to source of fusion, and that's about the sheet lamination process. This is about single stage, single step metal 3D printing is possible predominantly with the 4 processes. And if you talk about the multi-step, say, by any way I need to get the metal part getting printed. So I have only even I'm with the VAT system can also be done. Ceramic or even a metal can also be done, right? So, but how do you do that? So I'm not going to explain these steps, and I don't want to get you bored. But the idea here, keeping this slide is, so it may not in a single step you're going to get the metal part, but you may get a green part, or you may get the combination of polymer plus metal, maybe some composite material which joins your polymer as an adhesive. So you have addition as a polymer with a metal plus powder, metal plus polymer. So then you take that green part and use the furnace treatment. So you make it brown part and keeping it in a furnace and do debinding sometime. And sometimes we do infiltration, or sometimes we do not do infiltration. So what I'm trying to say, by using a secondary process, your green part or your composite parts can also be made as a metal, 100% metal component. So with this background, so let us talk some of the metals. Why? Because our talk will be focusing on the metal. So if you talk about the iron-based, iron group of your metal alloys, so you have stainless steel 316 and 316L, and it can be done directly with the powder bed fusion or a DED system, that is direct energy deposition and binder jetting technology. I'm talking about direct, but indirect or secondary, even it can be possible with even the VAT system also. But I mentioned here as a single step process for processing this 316, 316L or 304 or 174 pH or 18300, 155 pH, 420, 347, 1033, 4130, 100 steel, even tool steel, H13, 4340, M2, and we do have other, say, iron or the steel or the alloys, Invar and carbon steel. You have a series, and even pure iron can also be processed through either a powder bed system or a binder jetting system. So these are the well-known iron-based alloys. And coming to the titanium-based alloys, you have a commercially pure titanium, which it can be processed through any one of these 3 in a single step I'm talking about. And Ti-64 is predominantly used for medical, aerospace applications, and even is ELI, 64 ELI or gamma Ti aluminum is a titanium-based alloy that predominantly used by using these metal 3D printing systems. And aluminum is another alloy where you can make use of 100 series, 1000 series, 2024, 6000 series, 7000 series, and you have silicon magnesium like 10Mg, 12Si. So you have a different aluminum-based alloys, and nickel-based Inconel 625, Inconel 718. You have Renal 42, and you have other nickel-based alloys, Hast alloys also, and refractory. So you have refractory tungsten, tantalum, and you have cobalt, chrome, molybdenum, alumina, stellite, and you have tungsten, tungsten carbide, and you have even copper based. Now this is a recent addition into the 3D printing material, that is a copper based. Pure copper can also be processed, and it can be a copper based alloy, or even it can be a precious metals. So right from the gold, silver, platinum, palladium, tantalum, which it can predominantly, the powder bed fusion is a predominant, and even here and there some DED and binder system can also be processed. And magnesium based, pure magnesium, magnesium aluminum, and you have other magnesium based, and like bronze, neopium are like, these are some of the well-known metals that is getting printed through a 3D printing technology. So with this background, we'll see the advancements of these processes in with the perspective of material, that is metal printing, right? And of course, let us start with the VAT-based system. Why? Because this was the technology, the 3D printing journey started with a process called SLA, which Chuck Hull has invented this, that is based on the VAT-based system. So the VAT-based system, so as a single step, it may be only polymer or the plastic, that is epoxy resin. So that is which you will be curing your epoxy resin or photosensitive resin through either a laser. So laser was the initial energy source. It has been started, but now even a DMD, that is a digital micromirror device, or even it could be an LED or LCD based projector system can also be used here with the initial energy source was only a single point laser beam, so which obviously the build time is high. But why? Because it is processing point by point, and with the advancements where you could able to do it, the entire layer curing can be done in a single go, creating a mask, and then just so it may be a 40 times or 30 times faster than an SLA based a laser based system to a projector based or to an LED or LCD based technology, right? So but still the material is the epoxy resin. But why I've kept this here under the title metal printing, I will come to that. So you can produce a metal or a ceramics even through an SLA or a DLP based technology. How it is possible is, so your photo resin has been mixed with the ceramic powder or a metal powder, and which thoroughly mixed, and that mixed slurry, you prepare a slurry and you send that slurry through this tube, and the working principle is same. You have a projector, I think, which you can see right now. This video is showing, demonstrating. So you have the slurry of this resin plus ceramic, or same case for the metal also, which the projector is getting projected here. So the each cross section, so it has been, say, initially it get printed, and further it has to, I already said, it is a multi-stage process, multi-step process. So that's what we need to do, a debinding of this the plastic binding elements that are there in the material that you have started, and then finally it should be subjected to a sintering step in a furnace. So you sinter that. So once you sinter that in a furnace, and finally you are left out with your ceramic or metal part. So this is a two-step process or this is basically your ceramic parts or metal parts can also be printed through a VAT-based system like SLA or a DLP. So this is one where we can talk about the VAT-based system, the scope of metal printing in a VAT-based technology. And then we'll move on to the next technology as a material jetting. So I hope the previous speakers might have given a lot of insight about all these processes. But again, I am talking you like there's a metal, the possibility of printing with the metal. So which you can see, though this technology has started with the plastic printing or plastic jetting, the epoxy resin, which the previous VAT system is also used. So instead of taking it VAT, you will be jetting from the nozzle, right? That is only the difference, but it works with the same chemical bonding, that is a polymerization process. So that may be the case for the epoxy resins. But what I'm trying to say here is you have a recent advancement under the category of material jetting called a nanoparticle jetting. So from the XJet, so even you can do a metal getting printed through a material jetting system. So then you will be curing with the heat rather than you're not using any sort of light or you're not using any sort of laser here. So you may be jetting through or curing through a heat. So you will be depositing this metal, you bring it in a droplets. So, and then use some sort of heat energy to melt that rather than to solidify that and get your component. So then we'll discuss, next slide will tell you. And then even you do have this wax is also possible. I think the previous speakers might have discussed that, but our intention should be on the metal side. So you do have a beautiful polymer based products, but coming to the metal and ceramics, even it could be done, but not in a single step, but again it could be a two-step process, which you could even able to print the metals or the ceramics through this material jetting system. How it is, so then we need to say metal should be jetting it. That's quite funny, it seems like, which it should be even, which you generate you create your nanoparticles that is getting added into your the liquid thing. And here you have a support as well as model material also, and which you will be starting with taking a CAD model, slicing, supports, all that stuff. And the thing which we need to do here, the preparation of material is quite interesting here, and that's quite tricky, and which we need to say jet this material. Then you have say nanoparticles which has been suspended and which it is jetting from the nozzle, 2 micron layer thickness, and which we can see. So it is jetting from that nozzle, and it is getting, and depends on the temperature, means what kind of material that you are processing it, maybe steel, maybe aluminum or titanium or whatever material that you are trying to fabricate it or trying to jet it out. So then that depends on your the heat energy source that you are going to use that, and then correspondingly which we need to maintain that temperature, the melting point temperature, that. Or even aerosol jet printing is another technology where even, let me see if this will work. So even it could be an aerosol jet process, like where you will be atomizing, you create a sort of atomized, the material is in the form of a droplets, they will call as aerosol. So that aerosol is being prepared and it is being atomized in an atomizer, and which it is getting say sprayed from this. Then once it got sprayed from this thing, and which it is going all the way to this orifice to this side, and where you have to remove some of the gases that has been which you need to do a sort of so evacuating, removing that excess gases to to create this aerosol mist as very dense, and which you will be doing here, which you will be removing those gases, and finally it is getting very dense aerosol. And obviously, being a jetting system, which you will be depositing from through the chute gas, then you will be jetting this aerosol mist into this say from the nozzle head, so which it has been deposited. So in this way, where your electronic parts, your electronic devices, circuit devices, so can also be done by using this sort of technology. So like this, which it need not be restricted to a polymer based technology. So even it can be very well produce the metals also, right? So that is my intention to highlight here. And even sometimes it could be an electromagnetic pulses. So you take your raw material, say for example aluminum. So the aluminum wire spool has been taken, and you have an argon gas. Of course, oxidation is a major problem here. Instead of printing them through a powder bed system, so using some lasers, but here there is no powder and there is no laser, but simply it is a wire spool, aluminum wire spool, and no laser here. Just you are using the electromagnetic pulses. So that electromagnetic pulses, which it will be, say, melting your material. So, and of course, argon gas is a chute gas used here, and you have the nozzle, ceramic nozzle here is there, and which it is depositing here. The and we do have several challenges here. It is not that much easy, which you are talking about, your viscosity, surface tension, and other stuff. But people are doing it. It's gettable, right? So it is not impossible. People are doing it. It's possible. So even they are attempting to aluminum 660.3 centigrade is the melting point. As we know that titanium is 1600, 68 degrees, 68 degrees centigrade, and iron, chromium, and other say whatever may be the melting point of your metal that you are going to targeting it, and you maintain your pulses, and through the energy regulation, or you maintain that, and then company like Xerox has been acquired this technology, and it's a recent development. It has been come to the market very recently. So this is about the material jetting technology for metal printing, and even binder jetting is equivalently good to print metal parts, but need not be a single step, but it could be a two-step process. Though this binder jetting system started with the polymer as well as gypsum, sand kind of a material, but even metal is also quite say gettable, printable. The metal is also printable through a binder jetting system, and this binder jetting system has originated from MIT, the great university MIT, and they sold the patents to 4 different companies like Z Corp, Voxeljet, X1, 3D Systems, so on. So, and as we know that HP, they are pioneers in 2D printing, 2D color printing, and even they have come out with a similar technology, but not exactly similar. So they have come out with a multi-jet fusion technology, but predominantly for plastics. It won't work for the metals, but our focus will be on the metals, so we will focus on that. So the name, it's a binder. You are going to sprinkle it from the nozzle, right? So simple. So which you will be jetting the binder from the nozzle, and you do have some this ink or the binders, which it has an absorbing sort of capability, and which it will get absorbed into your powder particles. Basically, the raw material is a powder granulates, and which your binder, or which it have an absorbing capability, and which it is getting forming a bond, and you do use IR light to do sinter it, and finally your sintered polymer. And similar it could be for the metal also, but not in a single step. We'll discuss that how you are able to get that say in case of a metal system. So metal system, again the working principle is same. So which we need to jet out the binder from this series of nozzles. So that binder will be jetting out onto the powder. The raw material is powder, and it has been laid in the form of a bed, and you will be sprinkling your binder onto this powder particles, and where you will be curing between the binding, the curing between the layers, and you get only the a green part basically, and that green part will be say depowered, and then finally it has been sintered in the furnace, and even it will be infiltrated with like a bronze kind of material. It has been infiltrated. After infiltration, after sintering, so which you can see this green part has become 100% metal part. So, but though it is not in a single step, as I already mentioned, so maybe sintering followed by infiltration could be the metal component. So as we know that this technology has been proven for the sand cores, making sand cores and ceramic parts, and of course polymer parts, and now it is the metals. And then you may choose the combination binder with your powders. Say you have a different binders here. So if you want to process metals, then I may use a polymeric binder. And then if I am processing ceramics, I may use an appropriate binder. And if it is simply a plastic or a plaster kind of material, gypsum kind of a material, just simply I use a water binder, or a sort of what you call aqua binder. So on, like which your the type of material that, right from the polymer to metal to sand to ceramic, and choose an appropriate combination of your binder, and things goes like that. So this is a typical binder jetting system for metals. And you may wonder why extrusion based is it possible to print metals. You may get some question in your mind. Why? Because 100% people, maybe if you know about the 3D printing technology, undoubtedly it is extrusion based system, that is FDM based system, that is a filament based FFF kind of a system. Why? Because it is say open sourced or DIY kind of printers, which after the RepRap movement, so then you have these printers as a open sourced, right, which you may be predominantly using a plastic, ABS, PLA sort of polymers. And recent times you have the composites also. You do process composites through this FDM based system. Even metals also possible. You may be exposed to this process, how it will work. I need not explain. Probably this may be the default printer wherever you can find. This is extrusion based printer, which you have the filament typically 1.75 or 2.75 mm diameter, two standards available with the filament, and you do say squeeze from the say you melt it and you deposit. Basically you a liquefied state, it will come and fall, and it will get infused one layer upon another layer. That's a common FDM based, and you have a model and you have a support material also, and which you may be very much familiar about these sort of Cartesian delta or other configurations of this FDM based system. So, but my focus could be on the metal side. So this technology is so far very good for a thermoplastic kind of a polymers, but now it is also for metal, ceramics, and of course fiber fillers or composites. So it is quite eminent in the recent times. And right now our focus will be on the metals. So how do you get printed your metals through FDM based system, right? Say instead of a filament wire, you start with a metal rod. So this metal rod, which is of 316L, or maybe any sort of metal that you're looking at. And again, I said it is not in a single step process. So it may first print it through the same principle, and we do debind it in a debinder, and then finally you do sinter it into the sintering furnace, and finally you have left out with your steel component 316 or any sort of say no laser, no powder. It's very more economical rather than the powder bed or a DED system, so which will cost you around say 4 crores, 5 crores of rupees. But this technology is quite interesting rather than more economical also. If you talk say cost to cost comparison of your parts versus powder bed and the FDM based metal printing, obviously, so it should undergo obviously printing, debinding, and furnace treatment. And let us focus onto the next technology, that is sheet lamination. So sheet lamination and scope of metal. So my perspective could be in that way. So I doesn't want to repeat whatever the previous speaker might have explained about these processes, but my intention could be whether the metal parts can be printed out from this sort of a particular sort of 3D printing technology. So sheet lamination, if you talk about, so it is ancient technology where we need to have the sheet of papers or a sheet of ceramic coated papers, or even it can be a polymeric binder coated, or it can be a typical soft material normally. And then it has been composites can also be, that is a thing, or even metals. So instead of paper, you take a sheet of metal, or the or maybe tape, a metal tape of say half-inch or quarter-inch metal tape, or even it could be anyway paper. That was the ancient technology which you may come across, a sheet lamination based LOM, that is a laminated object manufacturing. Is a very well-known process under this 3D printing technology. So you do print it in a different colors or different, basically that is a color of a paper, or even you can use some sort of ink to mix up these colors. Yeah, and then even you may use, you need not use a laser to cut a paper or a soft kind of a material. Then people realized even you can just use a knife to cut your papers, the kind of a material, right? And even right now you may be focusing onto the carbon fiber composites, so through a sheet lamination process. So it is quite gettable. So which it could be, say, start with the sort of say you prepare a laminate which it has been jetted, printed out from your sheet lamination based system, and finally you remove those things, and finally you're left out with your carbon fiber composite component. So that is through a sheet lamination based technology, right? So which and quite interestingly, as I already said during my previous slides, where welding, ultrasonic welding or solid state welding is also the sort of joining technique that you will be using in a sheet lamination process called ultrasonic consolidation. So where you can see it is an hybrid process basically, right? So you take the raw material as a metal strip, so maybe copper, maybe steel, aluminum. So what sort of material you bring it in the form of a tape, so which you can see those tapes, or even getting it by the CNC milling. It's a hybrid process, as I said. Like you do a certain tires, maybe 10 tires with the contour milling, and then followed by, even it can be through welding technique. Basically, why it has fallen under the additive manufacturing, so which you will be adding these, or layer by layer, which you will be and joining it through an ultrasonic sonotrode or ultrasonic welding technique. So it is an hybrid process where you will be combinedly milling and then joining through welding process. So basically, you start with ultrasonic, say, motion through an oxides to break, and you create a localized, so it's to collapse here, and then you have the heat and pressure which create your high strength solid state bonding between the the laminates, or the wire, or whatever it is, tape or whatever it is. And even the biggest advantage of this process is, even you can go with metal matrix composites. So you can have aluminum and you have a titanium laminates can also be done through, or even it could be an alumina fibers in the aluminum. You can form an MMC, or even it could be a silicon carbide fibers, so which it can be embedded into your sort of base material. So which it could, even you can generate a functionally graded materials also through this technology. So this is about the scope of metal printing under the sheet lamination category of 3D printing. And then powder bed, it is well known for metals. So whenever you talk about metal printing, and this guy will be the guy which will comes into our mind. So that is a powder bed fusion system. The powder bed fusion system, of course, it has been started again with the polymers, but not the metals. So that is with the Scott Crump, the Texas University guy. So where he filed the patent, the Carl Decker has filed the patent on the process called SLS. So so the patent got expired, and now the SLS technology, that is a partial melting, which we used to have the binder as coated onto the powder particle. So that was the technology for the polymer, or even for the metal, or for the composite. But slowly that has been modified by the German technology. Why I am quoting this is, though this technology has started with SLS based technology with the polymers, but this metal printing has inclined towards German based technologies, where you can find a lot of German or a lot of European companies has developed, either through the proprietary name as a DMLS or SLM, but basically it comes on the powder bed classification. So as we know that again, you may use either a laser as an energy source or an electron beam as an energy source. So this is a very well-known metal printing system. Over the period of time, it has been say established. Yeah, and need not be an economical solution. Why? Because it may be a costly machines. These machines are very costly, but yeah, in the recent times the patents also getting already expired. The key patents of powder bed system for the metal printing is also expired, which we can find some sort of open source or some sort of say, definitely we can see the scenario as we are enjoying right now for the FDM based system. But not up to that level, but some extent which we could. Why? Because this technology requires a laser or an electron beam or any sort of energy source. But like FDM system, it doesn't require such sort of component, but it may be more economical and more cost effective. But here, but definitely it is not 4 crore or 5 crore. Once you have a laser with a 100 watt or a 200 watt laser, which you could be able to integrate, and people are already started to develop their own metal 3D printing systems through a powder bed system. I know at least a couple of people are already bringing their product into market. So, but anyway, so, and then which we will be talking about, I put some heading like advancements. And if you see the advancements of this powder bed vision technology, so the major help here is a supports in any powder bed system with the metal printing. So the major drawback, not drawback, or it may be a headache for us is a support structure, right? So then how do you make it a support free or with overhang angle maybe 10 degree, typically 40-45 we need to build a support. And again depends on it is a down facing or up facing, and again we need to have other headaches will come into picture. But anyway, the people are putting a lot of efforts to develop the own the advanced systems, which it will may simplify your support structure requirement or any complex structures can also be produced through. Or another problem with this is I have a slide at the end. I will show you the print rates or the what is the printing speed. Say what is the say how many kg per hour or how many grams per hour you are going to print. What could be the speed? So definitely it is not that much great as in terms of speed is concerned. So definitely people are looking to have minimize the setup time. Say you cannot simultaneously recoating the powder as well lasing the laser. You cannot do that. We need to wait for recoating system to recoat the powder, and then only the laser has to say fuse or the melt, or it has to lace the material, the powder material. But it will take a lot of setup time, and then people realized, so can it be done simultaneously? So and then that is what, and anyway dual laser and other number of lasers has also increased, and which increasing the productivity. But that is not a good idea. Even we can reduce a lot of setup time. So that is another idea where people are working in that direction to develop the new systems, which it may be 55 times faster than the existing speed of the powder bed metal printing systems. So then a lot of efforts are on to increase the productivity. And let us come to the last process, that is the directed energy deposition. So this is again, it is very close to the welding technique, right? So where you can find your TIG welding, so or MIG welding. It's very similar to a TIG welding process. So, or you may come across the laser cladding, right? So where this directed energy deposition, it is predominantly for metals. So it is a single step metal process. it is predominantly metals, and where you can fuse with the laser or electron beam or plasma, or basically this is where you will be say using a high power laser, and you will be supplying the powder from the nozzles through carrier gas, and you have an inert environment inside, and you will be consolidating the layers. And of course, again, you have a lot of freedom here. So the 5-axis freedom, that will some extent say reduce your efforts towards a support structure generation. So you have the more degrees of freedom. So you do have either use a laser energy or electron beam energy, and you may use a say powder as the feedstock, or it can be a wire, a blown wire, a blown technology, powder blown, or even it can be a wire fed systems. And wire arc additive manufacturing, it is very similar to the TIG welding process. So where even people are aiming to fabricate very big sized structures, maybe even fuselages, people are targeting to print through this DED system. So even you do have a certification from the Federal Aviation Authority for certifying them that are used in an aircraft, like maybe Boeing or Airbus or maybe GE, or either for the structural components or underhood components, maybe for jet engine components, nozzles, or any other jet engine components, like people like GE or people like Rolls-Royce, Pat Whitney. So then they will be much focusing on at least two technologies, that is a powder bed system, and another one is directed energy deposition system. So where you can have basically it is a near net shape process, as we know that. So even you can increase the build rate, but wire will be having its own challenges versus powder. But the production rates, definitely you have a better if you have a wire fed, and that too it is an electron beam. So you try to understand a laser is bit slow compared to electron beam, but controlling electron beam may be challenging. But anyway, and that is the source, energy source, and as well as the feedstock is concerned. Again, you have a powder and you have powder versus wire. So wire may be a bit faster, as we know that, rather than a powder handling challenges or other stuff, which even it can be wire with electron beam. It will be a good combination where you can even increase the productivity. So, or even the big sized components can also be fabricated. So yeah, and which we can see the build rates of different metal 3D printing processes. So here I mentioned only two process, that is powder bed and as well as DED. So of course this I have took from the literature. So where you can see the build rate, that is kg per hour. So the kg per hour, if you talk about the laser beam in combination with the powder bed fusion, laser beam is energy source and powder bed fusion is the type of process that it could be around 0.2 kg per hour. But if you replace the laser with the electron beam, so now it is 3 kg per hour. And if you talk about the DED, DED with the powder, it is almost equivalent build rate it is giving. And which you have laser with a wire, but I got a doubt. But anyway, we should rely this source. But anyway, so with laser powder combination, laser with the energy and the powder as the feedstock and DED as a system, it is 3 kg. And again laser, and you have a wire and DED, so again it may be 3 kg per hour. And you have an electron beam as an energy source, and you have a wire fed, so then it may be a 9 kg per hour. And this is EBM I'm talking about with the wire fed. And you have a wire arc with the AM system, that is a wire arc, wire fed. So it is almost like 18 kg per hour. But it may not be comparable with a strip arc cladding. So it may be going around 50 kg per hour. So, but still what we can conclude is, but the build rate is not that much great as we are talking about, but the accuracy is very good in terms of the power bed systems versus DED systems. But you will get a near net shaped things, but it's very faster. Yeah, so in that way, which we can. And before concluding, let us focus some of the challenges, the 3D printing fabrication challenges, so that you come across. But we cannot generalize these challenges. So why we could not generalize the challenges? As we know that polymer will behave differently and metal will behave differently. And then you do have a different feedstocks, right? And you do have a different energy sources. But definitely we have a lot of fabrication challenges. It is not that much easy as we are seeing one side of the coin. So we do have a first challenge, maybe standardization of your process. Like you cannot find much of the ASTM or ISO standards to standardize your process or a feedstock or testing or whatever it is. So you have a very few standards got published in this area. So then how do you ensure that you are getting a good part or a bad part? Why? Because machine to machine, you have a lot of variation. You cannot get consistent result. Maybe run to run also there will be variation. So then the reasons may be several. So right from your the feedstock, the source of raw material that you have been, whether it has been as for the standards, typically. Why? Because what could be the grain size and what could be the grain shape and what could be the flowability and things like that, right? So where even it will dictate a lot on your quality aspects. And you do have a process controls and error correction mechanisms or very poor, or say, though this technology is existing for the past 20-25 years, I'm talking about metal, though this technology is existing for the past 30 years, but metal printing is relatively maybe 20-25 years at max. So where we need to standardize these process controllers, and we need to do a lot of stuff, but it may be lagging it here. And the post-processing requirement may be another challenge. Like as I said previously also, sometimes it may go 50%, 60% cost, total cost, the post-processing cost may contribute. So it will be having a lot of impact on your cost, time, and quality. Why? Because so your post-processing is the another challenge. And then certification. So you don't have much standards, then how can you expect that somebody will come and give a certification on this, right? So then you can find the difficulty in somebody is getting certified and somebody is getting qualified for your usage, right? So then how do you distinguish whether if somebody is certifying it's ISO certified or it is as for the ASTM standard, something like that? somebody is certifying. For example, like medical application, you have an FDA or any sort of regulator has to certify, or like FAA, like in case of aerospace applications, so somebody has to certify, right? But still, the users, they are collaborating with the organizations like ISO or ASTM. So they are developing their own qualification and certification in collaboration with these organizations. But still, it is very few. But still, it should be explored. And new potential health hazards to the operators, that is another issue, especially the powder bed based processes. And say integrity of your digital data and a lot of threat for your data. Say cyber security or the blockchain technologies should be further, say, here should be developed, and where it is lacking here. And of course, IP, the IP protection. So like that, keep on, we can say several challenges we can throw. And say broadly, if you say take each and every aspect, right from the material type, the powder size, powder purity, and so on and so forth, and design side, so the geometry or the overhang support structure are designed for additive manufacturing, so support structure, overhangs, and other aspects, right? So which we need to. And of course, layout aspects, like you have horizontal, vertical orientations, and object proximity, chamber filling, and other challenges which you come across while fixing your say build setups. And then while processing hardly, you may have roughly around 180 parameters, so that may dictate your quality of the parts that you are getting fabricated. And again, you cannot standardize, so you cannot take the conclusion based on, say, you have conducted some experiments, and then you cannot generalize on say steel powder you have done something, and the other time you are using a titanium powder, and some other time you may be using a inconel. But you cannot standardize those parameters, which it will behave totally different. You have a titanium is a reactive material, and whereas steel is not a reactive. But how do you correlate your parameter set, right? So then that is the issue, like where we need to, every time it is a challenge for you guys to work on these, optimizing the and developing the parameter sets for each and every material, new material that you are developing, right? So, and of course, post processing, as I said, like heat treatment, short pinning, polishing. So which otherwise you can minimize these effort by some extent with your design for additive manufacturing philosophy, if you follow, right? And then you talk about the defects or the concerns or the kind of surface tension or the viscosity. You can encounter a lot of problems like a curdling effect or shrinkage, warpage. So that is due to an residual stresses which it has been developed inside, and you have a lot of temperature gradients, right? So, and heat dissipation and staircase effect, which you can normally come across these sort of staircasing errors or the problems. Anisotropy, that is another issue, so which you cannot get an isotropic property across all the directions. You cannot get, as we know that it is stacking in Z direction, so you cannot expect the isotropic properties in all the directions. And volume contraction, micro melting. So you do have a lot of implications to work on this. So it is the other side of the coin, right? So where you may be, and then to name a few common defects in 3D printing. So and this is a very big subject to be discussed, but like where you find some literature in this direction, where you can find a lot of defects, like it may be a balling phenomenon. So balling phenomenon, it may be due to your what you call due to your the solidification is not happening. Say if the solidification is too quick, it may lead to other problem. If the solidification is slow, and it will be ending up with forming some balls. So that will be because of that is basically because of the surface tension, so which it is no dominating your the fluidity of the metal that you are trying to solidify, right? So you do have a balling phenomenon, and you can find some keyholes. That is because of your say penetrating your it's a plasma, or if it is any energy source that so then how do you say adjust these process parameters? That is going to be your energy density. So then, and sometimes you have your material get degraded, like say chemically it can be degraded, or especially if you take a polymers, or even powder also, which it can be, of course, oxidation. That is the biggest issue, where though you will be inerting it, so everything you will be doing in a inert environment. Typically you may use nitrogen or argon gas, but still oxidation is the major culprit. And you do find some cracks inside your 3D printed structures, and delamination. It may be from the substrate to your layer, or among the layers, which your layers getting delaminated, maybe because of your shrinkage or warpage, or even distortions also we can find. So because of these issues, so the temperature gradient or the internal stresses, the residual stresses inside it has been developed within the layer or at the interfacing of two layers, or so on and so forth. And you can find some inclusions and poor surface finish. Definitely, it is not on par with the conventional processes as built I'm talking about. So as built components, so we cannot nowhere comparing with the CNC, especially I'm talking about, but it may be on par with casting, maybe in between casting and forging, where you can place this technology, but still the surface finish is the major common defect that you can find. Then reasons are several, so you cannot generalize, as I already said, like which you can have a different phenomenon, different behavior versus your raw material to the energy source. So, and porosity is another major concern. So where because of oxidation, or because of entrapped gases, or maybe several reasons, so which you could not get 100% dense, and further you may be going with a hipping sort of post-processing method, and so on and so forth. So then you can find several defects which somebody is looking for some research problem. So definitely it's going to be very interesting stuff, where you have a lot of scope to do a research in metal printing, or in general 3D printing as such. So right from the your design aspects to surface structures, to topology optimized structures, to your process parameters, optimizing the process parameters, to your whatever these common defects which you can focus. You can pick one defect and you attack onto that, and then you made some samples and do even conduct a lot of research on these areas, right? So somebody may be looking for, I hope the previous speakers also might have given a lot of research problems to you. You can have a lot of scope to work on this, and we do simulate it, right? The simulation is another area where even you can focus. You can create some multi-physics kind of multi-scale modeling, so where you can predict the model distortions, or the residual stresses that has been built inside the layers or substrate to layer or like that. And you can even suggest some sort of compensations also through your simulation studies, and do have a model optimum support structures, or which it will create a minimum risks to a printer damage or a recorder damage, which you could able to do a better simulation stuff before you blindly running a code, firing the component onto the machine. So, and minimize the number of build tryouts, and which will even predict some post-processing requirements like heat treatment or heaping or support removal and so on and so forth, and which we can optimize even through simulation. You can optimize the build orientation, support configurations, which you can say operating conditions on sort of your distortions or a sort of plastic strains and residual stresses, which you can take up one of the research problems. It's a burning a topic in this area where you can target on the residual stresses, the sort of thing which you can work on this. And before concluding and handing over to the organizers, just even you may be curious, I have been talking about standards are not there, standards are not there, but how many standards are there as published so far? So we can find hardly around 35 to 40 standards. It has been already published, and another 35 to 40 has been under development or under trial or under evaluation. So which you can see some terminology related standards, which it is ISO and ASTM combined development, which for the terminology you have specific numbers and standards for that. And if you're looking for some design aspects of the standards from ISO as well as from the ASTM, so which we can see some of them are combined effort from ISO and ASTM, or some of them may be independently. ASTM has developed certain standards. And coming to the design guidelines or the general design guide, so which you can refer ASTM 52910. And if you're looking for the powder bed design guidelines exclusively, and then you can refer 52911. And if you're looking for DED design guidelines, I said like you cannot generalize these guidelines, right? So you have a DED system, you have a design guidelines 52922. And if you're looking for functionally graded design for functionally graded materials, and you do refer ASTM 52912. And material extrusion design guidelines are also there, and for post-processing design guidelines also there. You refer ASTM website also, but it is not an open source which we need to pay them. Just you could able to download, you can download. And then you can have certain data format, like STL is a de facto standard, but need not be an ideal representation where you have AMF format has been developed by ASTM 52915. And you do have a purchase AM parts like from a service bureau. You should not get cheated, right? Say, then if something goes wrong, whether you can check whether it's as for the ASTM standard, and you can file a sue against the service provider or the service bureau, right? And you do have AM fabrication related as per specimen testing F2971, and mechanical properties for metals F3122, and cobalt chrome part properties F3213, and thermal post processing 3301. F stands for F reserved for additive manufacturing for ASTM standards. And you have F42 committee also looking all these things. And titanium via power bed fusion, you have 3302. And test artifacts, geometric capabilities, it's a combined effort from ISO and ASTM 52902. And you have terminology, that is 52921. And feedstock. For feedstock standards and powder characterization, you have F3049. For titanium 64 grade of titanium Li, that is F2924. And ELI kind of a composition that is F3001, Inconel 718, that is F3055, Inconel 625, F3056, stainless steel, you have F3184, and aluminum 10 magnesium, that is 3318. So like that, you can find other standards also around 35 to 40, which it has been already published. Let me summarize what I have done for the past almost 2 hours. It is touching. So we started with the various steps in the 3D printing process and some workflow of metal 3D printing technology, and we discussed some of the material options and then processes and with the perspective of metal printing. So all the 7 processes we have discussed with the perspective or possibility of metal printing, and fabrication challenges also we have discussed, and some common defects or errors also we have discussed, and the state of art of standards in 3D printing. So that also with a single slide, I hope I have communicated to you. And before handing over to the organizers, we have a facility. So we are running additive manufacturing course first time in India, MTech specialization, and we do have a metal 3D printer of powder bed technology, that is from 3D Systems DMP Flex metal 3D printer. And we do a couple of Stratasys make FDM machines right from the Dimension to the Mojo. And we do have a desktop printer like Ultimaker 2 Plus and other DIY kind of a printers. And we do have AnyScan, SenseScan for scanning facility, and muffle furnace and short pinning machine for post-processing of this metal 3D printed parts. And we do have softwares ranging from Mimix, Magix, Trimatic, Catalyst, and 3D Expert software. I think I have done from my side, and I may be the happiest person if you suggest me the presentation, as well as you correct me if you have any mistakes, if I have any mistakes, or if you have some clarifications or some suggestions. Yeah, definitely you are most welcome. So it is over to you. And we are running one YouTube channel, and if you are interested, even you can visit us, and you can subscribe us also. So I have pasted the link in the chat box of our YouTube channel. Okay, thank you for your patient listening. Right, so over to you, Dr. Paul.
Yeah, thank you very much, sir, for the nice presentation. And as you have mentioned about the all aspects in 3D printing in detail, and we are very happy to see the facilities that you have set up in the NIT Warangal, all the facilities in 3D printing. And we would like to know whether these facilities are open to research scholars outside, or it's only for the inside.
Yeah, right now we are using in-house, but if there are some requirements to the consultancy also, we can do it at the nominal prices. That can be done also. Yeah. So far, we are using it for the in-house research and the our academic purpose, curriculum purpose. We are using it. Yeah.
Okay. Participants can ask questions by direct unmuting. You can ask with the resource person who is available. So you can ask questions. Open to the participants.
Any questions in the chat box?
Yeah, in the chat box.
What can be the inspection methods for the products? A brief idea.
Yeah, inspection methods. Can you be elaborate, like what kind of inspection, destructive or non-destructive sort of inspection, or like there are no, as I already said, the ASTM, you can find some standards, but very few, 1 or 2, but still it can be the other inspection methods which you follow. But coming to the standards, which it should be evolved. It's any inspection methods you come across, maybe destructive or non-destructive type, which you can even do that. But standards still have to be evolved. Yeah.
Thank you, sir.
Yes, sir. Regarding this metal 3D printing, sir, how about the mechanical properties when you make a casted model and a 3D printed model? Like, there will be weight reduction will be there, but proportionally, what about the mechanical properties? What will happen to that strength, toughness? A lot of properties are there. How it is it compensated or it is a defect for metal printing?
Yeah, it's a very good question. Actually, as I already said, it should undergo some sort of hipping post-processing methods, like a hipping if you're not satisfied with the density that you're getting it, or porosity it's there, and which it can be compensated through a post-processing method some extent. Yeah, it is on par with casted parts. We can achieve the properties. Yeah, it's on par with casting we can achieve.
So what about the size? Is a limitation? So like casting, we can make big sizes. What about this
Yes,
one?
yes. If you talk about the powder bed systems, definitely the size you have a limitation. Typically, it could be around, though you have some build volumes around 2 feet or 3 feet, but rarely you can find that sizes of powder bed components. But DED, relatively, you have a good sized build volumes which you can get it from DED based metal printing systems. But powder bed still, it may be restricted to 2 feet or 3 feet by 3 feet by 3 feet maximum. Okay, yeah.
Okay, so what about the time taken, sir? Like how much we have the polymer based FDM are there. SLA also we have some basic stuff. So we used to take one small wire, say 3 centimeter. We take 8 hours in SLA. So what about this metal printing? The time, how much it will be taking for?
Yeah. Again, as already I have given some idea in one of my slides showing that the build rate, typically it could be, as you said already pointed out, it's time taking process, like 0.3 kg per hour is the rate. Typically 1-inch cube, if you try to build through a powder bed system, it is around 3 hours or 4 hours typically. Yeah.
So
Yeah, it is not that much fast.
It will take one day if you are going to a big site.
Yeah, that depends on the geometry and other features that are there. Yeah. But it's a slow. It is not that much fast, which you can. Yeah, but still there should be a lot of scope to increase the rate of production. Yeah, but still it is, especially metal printing is, as you said, like FDM again is a very slow process, but you have a DLP based technology and clip based technology for the polymer printing. So it is 40 times faster than the FDM, but it will produce almost the same polymer. It is 40 times faster than the FDM based technology. Yeah.
Okay, how we can compare the costs? Like, is it bulk productions required to compensate the cost? Like, it will be very costly, right? The equipment cost itself is very big. Then the production cost again comes. How can you manage this cost with the normal production?
Yeah. So first we need to understand the how many number of components which you are looking at. Like it is not meant for mass production, as we know that, and even it is not only mass production. It is not meant for even a reasonable lot sizes, but it is maybe a specific requirement where we are looking at some sort of complexity and some sort of difficulty in a conventional manufacturing methods. As we know that the complexity increases, the conventional manufacturing methods, the cost will exponentially increased, but which we can justify wherever you have more complexity, and which otherwise it cannot be produced through conventional methods, and where you need to have a lot of customization involved in your products. So then only cost-wise can be justifiable, but it cannot be. If you're looking for head-to-head, if you compare with the conventional manufacturing systems like machining, but it is not. But which we need to the conditions applied, right? you need to see these circumstances wherever you need some customization. Looking for relatively less number, quantity is very less. Yeah.
Is there any commercial products 3D printing, metal printing is available in the market? Like any commercial products from metal 3D printing?
Yeah. You can find the service bureau or like products you are talking
Products.
about. Products you can find several like aerospace industry where even people are even printing 1/3 or half of the components, jet engine components they're targeting to print through metal 3D printing systems. And medical implants is another area where metal printers are directly used to print the implants for the biomedical applications. Like that, where you have specific tooling requirement can also be explored this for making some injection molding dies or die casting dies. Even you can have a tool steel as a material option, so you can make die inserts for tooling applications. So where you can bridge that gap. You are asking about like how it could be for the mass production, but at least you can make a die for an injection molding machine or a die casting machine, so which it could be used for.
Yes, sir. So once we would like to know what are the current research areas you are working on this 3D printing. And
we are working on the various material side development and parameter optimization for various metal alloys, and medical research we do for implant design, fabrication, and placement. But this time I am not presenting here those case studies. Actually, we do collaborate with the hospital people to serve for any customized implant or personalized implants for patient-specific requirement.
Yeah, that's fine, sir. Very nice to hear from you, sir. So from participant side, if any further questions are there, we can ask now, or we'll come to the end of these sessions. I think anyone want to unmute, you can unmute now and ask questions with Professor Ravikumar. I hope there is no further questions. So once again, as far from the organizer side, as far as from our institute side, we thank you very much for spending your precious time with us and explaining the vast domain of 3D printing, which is quite unknown to many of us. And it is very interesting to know especially your slides shows vast variety of options are there in 3D printing. So we only know initially it is there, 3D printing is there in metal, and the cost was so many crores. So, but now we know it is not a single area. It is a very like an ocean. It is a very big area, and a lot of research is still pending in that area. And we hope many of the scholars who are attending this program will be able to cope up with the challenges faced in the metal printing. And we hope to communicate with you in future also, sir, like in this area, so that we can work and we can take your help and hope to come to an institute sometimes if the pandemic situation is getting over. So once again, thank you very much, sir. Thank you.
Thank you for the opportunity.
Yes.
Thank you for the
opportunity.
opportunity. Thank you. Bye-bye.